Imagine standing at the entrance of a cave, somewhere in what is now Austria. The year is 30,000 BC. The fire you carry is the only thing between you and the darkness ahead. You step inside. The ceiling rises, the walls close in, and then you see them. Bones. Thousands of them. Skulls the size of oil drums, leg bones thicker than your torso, teeth that could snap a femur like a twig. This cave was not abandoned. It was a graveyard, and whatever filled it was not gone. Not entirely. Somewhere deeper in the mountain, something was still breathing. This is not a story from a horror film. This is the true history of Ursus spelaeus, the cave bear, a creature that dominated the caves, valleys, and forests of Europe for over 300,000 years. An animal so massive, so deeply embedded in the landscape of prehistoric Europe that early humans built entire religions around its bones. A beast that stood taller than a grizzly bear at the shoulder, that weighed as much as a small car, and that left its mark on the walls, floors, and ceilings of hundreds of caves across an entire continent. And yet, it vanished. 24,000 years ago, the cave bear disappeared from the face of the earth, completely, without a trace of living descendants. One of the most successful large mammals in European history, gone. While brown bears survived, while wolves survived, while humans not only survived, but thrived. Why? That question has haunted paleontologists for nearly 2 centuries, because the cave bear was not weak, it was not small, it was not poorly adapted. By every measure, it should have outlasted almost anything else walking across Ice Age Europe. So what happened in those final millennia? What force, or forces, erased an animal that had survived glaciations, volcanic winters, and the complete reshaping of an entire continent? The answer involves climate, teeth, cave systems, and a species of primate that had recently arrived in Europe carrying spears. The answer, in other words, involves us. But to understand how the cave bear died, we first have to understand what it was. And what it was is far more extraordinary than almost anyone realizes. Stay with me, because this story goes deeper than any cave. To understand the cave bear, you have to go back. Not 30,000 years, not 100,000 years. You have to go back nearly 5 million years, to a moment when the entire lineage of bears was still being written in the fossil record of the Northern Hemisphere. The bear family, Ursidae, is ancient. But it is not as ancient as people tend to assume. In the grand theater of prehistoric life, bears are relatively recent arrivals. They branched off from a common ancestor shared with pinnipeds, the group that includes seals and walruses, somewhere around 38 million years ago. For tens of millions of years, this lineage remained small, agile, and largely unremarkable. Early bear relatives like cephalogale were no bigger than a medium-sized dog. Nothing about them suggested that their descendants would one day dominate the caves of an entire continent. The pivotal moment came roughly 5 million years ago, during the Pleistocene epoch, when the genus Ursus first appears in the fossil record of Europe and Asia. This was the ancestor from which all modern bears, brown bears, polar bears, American black bears, and the long-extinct cave bear would eventually descend. The world these early bears inhabited was already cooling. The long warmth of the Miocene was ending. Grasslands were expanding. Forests were contracting. And the animals living through this transition had 2 choices: adapt or disappear. The lineage that would become the cave bear chose adaptation. The direct ancestor of Ursus spelaeus was a creature called Ursus deningeri, the Denninger's bear. It first appears in European fossil sites dating to roughly 1 million years ago, during the early Pleistocene. If you had seen a Denninger's bear, you might have mistaken it for a large brown bear at first glance. But look closer. The skull is already beginning to dome upward in that distinctive way that would become one of the cave bear's most recognizable features. The teeth are already shifting. The carnassial teeth, the blade-like cutting teeth that most predators rely on, are becoming smaller, less prominent. The molars, by contrast, are growing wider and more complex. This animal is moving in a very specific dietary direction, and that direction is plants. This is the first great surprise of the cave bear story, because when most people hear the words cave bear, when they imagine a creature whose bones literally fill the floors of European caves, they imagine a predator, a killer, something that hunted reindeer and competed with wolves for carcasses. The name alone suggests menace. Cave bear, Ice Age monster, European nightmare. The reality is far stranger and, in some ways, far more fascinating. By the time Ursus spelaeus reached its full evolutionary form, roughly 300,000 years ago during the Middle Pleistocene, it had become one of the most committed large-bodied herbivores in European history. Studies of isotopic composition in cave bear bones, particularly the ratios of carbon and nitrogen isotopes preserved in collagen, tell a story that surprised even experienced paleontologists when the data first emerged in force during the 1990s and 2000s. The nitrogen isotope signature in cave bear bones is extraordinarily low. In ecology, nitrogen isotope ratios work as a kind of dietary fingerprint. Animals at the top of the food chain, apex predators, accumulate heavy nitrogen isotopes through their diet. Herbivores show low values, and cave bears, analyzed across dozens of sites from Spain to Romania to the Caucasus, show nitrogen signatures that in many populations are lower than those of horses and deer. Lower, in some cases, than almost any other large mammal from the same deposits. This animal was eating almost nothing but plants. Research published in journals including Quaternary International and the Journal of Archaeological Science across the 2000s and 2010s has confirmed this picture repeatedly and from multiple angles. The biomechanical analysis of the skull and jaw reinforces the isotopic data. The cave bear's zygomatic arches, the cheekbones, are dramatically flared outward, creating space for enormous temporalis muscles, the muscles used for grinding. The sagittal crest running along the top of the skull, where jaw muscles attached, is massive. The jaw itself could generate extraordinary crushing force, but oriented toward processing tough, fibrous, abrasive plant material. Roots, tubers, grasses, berries, possibly bark. A 2020 study from the University of Vienna, using three-dimensional geometric morphometrics on cave bear teeth, found that the wear patterns on cave bear molars most closely resemble those of giant pandas and other extreme herbivores, not those of omnivores like brown bears or wolves. The teeth are worn flat in a way that speaks to a lifetime of grinding-resistant plant material. Some individuals show dental attrition so severe, teeth worn down almost to the gum line, that they would have struggled to process food at all in their final years. Think about what that means for a moment. An animal the size of a small car, with a skull that looks like it was designed for battle, was spending its days grazing like a particularly enormous cow. But size deserves its own attention here, because the cave bear was not simply large. It was large in a way that demands specific numbers to fully appreciate. Adult male cave bears, based on skeletal reconstructions from sites including the famous Dragon Cave, Drachenhöhle, in Austria, and the Veternica Cave in Croatia, are estimated to have stood approximately 1.5 meters at the shoulder. That is roughly the same shoulder height as a modern Siberian tiger measured lengthwise, except the cave bear was not flat and horizontal. It was massive and vertical. When it reared up on its hind legs, a posture bears adopt frequently, a large male cave bear would have stood somewhere between 3 and 3.5 meters tall. That is tall enough to look directly into the window of a second-floor apartment. Weight estimates have varied considerably across different studies and time periods, as they tend to do with extinct megafauna where complete skeletons are rare. Earlier estimates from the mid-20th century placed large males at up to 1,000 kilograms. More recent and biomechanically rigorous analyses, including work published by researchers at the Natural History Museum in Vienna, suggest that the largest males were more likely in the range of 400 to 700 kilograms, with exceptional individuals potentially exceeding that. For comparison, the largest subspecies of brown bear alive today, the Kodiak bear of Alaska, reaches a maximum of around 680 kilograms in exceptional males. Cave bears were at the very least comparable, and in many individual cases, almost certainly heavier. The skull alone is staggering. Cave bear skulls recovered from sites across Europe are among the most commonly found large mammal fossils from the Pleistocene, a reflection of how many of these animals existed and how frequently they died in caves. A typical large male skull measures over 50 centimeters in length. The profile is immediately distinctive. That extraordinary domed forehead, rising almost vertically from the snout, giving the animal a broad, almost intellectual-looking profile that is unlike the sloped skulls of brown bears or grizzlies. The post-orbital constriction, the narrowing of the skull behind the eye sockets, is less pronounced than in many carnivores, giving the brain case more volume relative to the snout. Some researchers have speculated, cautiously, that this skull morphology may reflect slightly elevated cognitive capacity compared to other ursids, though this remains deeply uncertain territory. What is not uncertain is the physical impression this skull would have made on any human standing 3 meters away from the animal wearing it. Now, there is something else about the cave bear that needs to be understood before we go any further. Something that shapes every other aspect of its story. Something that is embedded right there in the name that we gave it. The cave. Ursus spelaeus does not simply mean cave bear in a casual, incidental sense, as in, we found its bones in a cave. The name reflects a biological reality. Cave bears were genuinely, deeply, obligately associated with cave systems in a way that no other large European mammal was. They did not merely shelter in caves occasionally, the way brown bears might den in a rock crevice or root hollow. They returned to the same cave systems generation after generation, century after century, millennium after millennium. They gave birth in caves. They raised cubs in caves. They died in caves in numbers so extraordinary that in some sites, the accumulated bones of thousands of individuals form layers meters deep. The Heinrichshöhle cave in Germany has yielded remains representing an estimated 30,000 individual cave bears. The Contarines cave in the Italian Dolomites, at an altitude of over 2,700 meters, contained remains of at least 1,800 individuals, suggesting that cave bears were accessing alpine cave systems at elevations that would challenge a modern mountaineer. Mixnitz Cave in Austria, sometimes called the Dragon Cave, produced bones from an estimated 30,000 bears excavated across decades of early 20th century work, making it one of the most significant paleontological sites in European history. These numbers are not simply impressive. They are ecologically significant. They tell us that the cave system was not incidental to the cave bear's life history. It was central. The cave was where the bear's year ended and began, where vulnerable cubs first opened their eyes, where old individuals went to die, where the hibernation that structured the cave bear's entire annual cycle took place. And hibernation, as we will explore in detail shortly, was not a minor footnote in the cave bear's biology. It was the engine around which everything else was organized. The teeth, the fat reserves, the diet, the timing of reproduction, the vulnerability to external pressures. Everything ultimately came back to the cave, which means that when something began threatening access to those caves, when the spaces the cave bear had depended on for 300,000 years began filling up with something else, the consequences would be existential. But we are getting ahead of ourselves. Before we reach the end of this story, we need to spend time in the world that the cave bear ruled. We need to understand Ice Age Europe not as a frozen wasteland, which is a dramatic oversimplification, but as a complex, dynamic, and often surprisingly productive landscape. A landscape where the cave bear was not a marginal survivor, but a genuine ecological dominant. A landscape that, for most of the cave bear's existence, belonged entirely to it. Close your eyes for a moment, and forget everything you think you know about the Ice Age. Forget the image of a barren, wind-scoured wasteland stretching endlessly under gray skies. Forget the Hollywood vision of a frozen apocalypse where nothing grows and everything starves. That picture is not wrong in every detail, but it captures perhaps 20% of the reality. The other 80% is something far more complex, far more alive, and in many ways, far more extraordinary than the simplified version we carry in our heads. Ice Age Europe was not one thing. It was many things, cycling through each other across thousands of years in patterns driven by orbital mechanics, solar output, ocean circulation, and atmospheric chemistry. The Pleistocene epoch, the geological period spanning roughly 2.6 million years to approximately 11,700 years ago, was not a single prolonged freeze. It was a long oscillation, a planetary heartbeat of advancing and retreating ice, of expanding and contracting habitats, of species appearing, shifting, fragmenting, and disappearing as the climate lurched between glacial maximums and warmer interglacial periods. During the coldest phases, the glacial maximums, the ice sheets over Scandinavia and the British Isles grew to thicknesses of 3 kilometers or more. Sea levels dropped by over 100 meters as vast quantities of water were locked into ice. Britain was not an island. Ireland was not an island. The North Sea was a broad plain of grass and frozen ground. Mammoths walked where fishing trawlers now drag their nets. But even during these coldest phases, the picture was not uniform. South of the ice sheets, Europe was not simply frozen solid. It was a mosaic. A patchwork of tundra, steppe, open woodland, river valleys with dense riparian vegetation, and sheltered mountain valleys where microclimates permitted plant growth that the surrounding landscape could not support. Researchers studying pollen records preserved in lake sediments and bog deposits across Central and Southern Europe have reconstructed this landscape in increasing detail over the past 3 decades, and what emerges is an environment of surprising complexity and, in places, remarkable productivity. The mammoth steppe, as paleoecologists call the dominant biome of Pleistocene Eurasia, was not a desert. It was more like a vast, cold version of the African savanna. Dominated by grasses, sedges, and herbaceous plants, punctuated by shrubs and occasional trees along waterways, it supported enormous biomasses of large herbivores, woolly mammoths, woolly rhinoceroses, cave lions, spotted hyenas, giant deer, Megaloceros giganteus, whose antlers spanned nearly 4 meters from tip to tip. Reindeer in herds that may have numbered in the tens of thousands. Wild horses, bison, aurochs in the warmer southern zones. This was a world of giants, a world of abundance and violence in roughly equal measure. And moving through the forests and mountain valleys of this world, following the rivers southward in autumn and retreating to the high ground in summer, was Ursus spelaeus. The cave bear's annual cycle was structured around a rhythm that would be recognizable to anyone familiar with modern bears, but pushed to an extreme that modern species rarely match. Because the cave bear's diet, so heavily dependent on plant material, was profoundly seasonal. In the temperate and boreal zones of Ice Age Europe, the growing season was short. Plants were available in abundance for perhaps 5 to 7 months of the year. For the remaining months, the landscape was locked under snow and frost, and the food sources the cave bear depended on were simply gone. The response to this challenge was hibernation, but not the light, easily interrupted torpor that some species experience. True, deep hibernation, the kind that drops body temperature dramatically, slows the heart rate to as few as 8 beats per minute, and suspends metabolic function to a fraction of its normal rate. The kind of hibernation from which a disturbance can mean the difference between survival and death. Because the energy cost of rousing and re-entering hibernation is enormous. Cave bears were, by the physiological evidence preserved in their bones, extreme hibernators. Research published in the Proceedings of the Royal Society B in 2019, using stable isotope analysis of cave bear tooth enamel from sites in Romania and France, found seasonal isotopic signatures consistent with hibernation periods lasting up to 6 months, possibly longer at higher latitudes and altitudes. 6 months. Half the year spent in a metabolic suspension so deep that the bear's body was essentially consuming itself to survive, catabolizing fat reserves built during the warmer months. This created an extraordinary selective pressure. Every single summer and autumn, a cave bear needed to consume enough plant material to build fat reserves sufficient to carry it through half a year of complete fasting. For a male weighing 500 kilograms or more, the mathematics of this are staggering. Bears entering hibernation may carry fat reserves representing 30 to 40% of their total body mass. For a large male cave bear, that is potentially 150 to 200 kilograms of stored fat, every gram of which had to be synthesized from roots, berries, tubers, and vegetation consumed in a frantic pre-hibernation feeding period that paleoecologists call hyperphagia. Hyperphagia in modern bears is already an impressive spectacle. A brown bear in the weeks before denning can consume 20,000 calories per day. It eats almost continuously, sleeping only a few hours, moving constantly between food sources. For a cave bear, larger, more nutritionally constrained by its heavily herbivorous diet, dependent on foods with lower caloric density than the salmon and ground squirrels that supplement a grizzly's pre-winter feeding, the hyperphagia phase must have been a period of extraordinary physiological urgency. An animal that failed to build sufficient reserves did not wake up in spring. The fossil record bears this out with heartbreaking clarity. Analysis of cave bear bone assemblages from multiple sites shows a consistent pattern, a disproportionate representation of very young bears and very old bears among the individuals who died during hibernation. Young bears in their first or second winter, whose smaller bodies struggled to accumulate sufficient reserves, old bears whose worn teeth could no longer process enough food efficiently, and a third group that appears across multiple sites, individuals showing signs of metabolic bone disease, osteoporosis, periosteal reactions, evidence of calcium mobilization from the skeleton during prolonged hibernation when dietary calcium was unavailable. These animals were not killed by predators. They were not struck by disease in the conventional sense. They simply ran out of energy before spring arrived. Now consider what this means for the cave bear's relationship with its habitat. The cave was not simply a place to sleep. It was a physiological lifeline. The temperature stability of a deep cave, typically hovering between 4 and 10 degrees Celsius regardless of external conditions, was precisely what hibernating bears needed. Too cold, and the metabolic cost of maintaining core temperature increased, burning through reserves faster. Too warm, and the bear's hibernation became lighter, more easily disrupted, and metabolically more expensive. The cave provided a thermal buffer that made the difference between survival and death across a 6-month fast. The specific geometry of the cave mattered too. Bears did not den indiscriminately anywhere inside a cave system. Excavations at sites including the Chauvet Cave in France and the Cotentin Cave in Switzerland have found evidence of preferred denning areas. Recesses, side chambers, deeper sections of the cave where disturbance was minimized and temperature stability was highest. Bears returned to these specific locations repeatedly. Scratch marks on cave walls and floors, some of which have been radiocarbon dated to over 30,000 years ago, record the physical traces of animals preparing their dens, turning in circles, scraping bedding material, settling into position. Some of these scratch marks are at heights of over 2 meters, made by bears rearing up and dragging their claws down the cave walls. Standing in a chamber in the Chauvet Cave today, the same cave that contains some of the oldest known human art on Earth, you can see both the claw marks of cave bears and the charcoal drawings of Paleolithic humans on the same walls. 2 species separated in time by perhaps only a few thousand years, leaving their marks on the same stone. That proximity is not coincidental. It is the heart of the story we are building toward. But first, because no creature exists in isolation, we need to understand who else shared this world with the cave bear, who competed with it, who feared it, who tolerated it, and who, eventually, would come to challenge it in ways that 300,000 years of evolution had not prepared it for. Ice Age Europe was not short of dangerous animals. The cave lion, Panthera spelaea, was the largest felid that Europe has ever seen, bigger than any modern lion, possibly the largest cat in the history of the genus Panthera. Males are estimated to have reached lengths of over 2.5 meters from nose to tail base, with body masses potentially exceeding 300 kilograms. Cave lion fossils have been found from Britain to Siberia, and the animal appears frequently in Paleolithic cave art, depicted with remarkable accuracy in the Chauvet Cave, where human artists painted a pride of cave lions stalking prey with a naturalistic precision that speaks to intimate, repeated observation. The cave lion almost certainly preyed on cave bear cubs. Whether it regularly attempted to prey on adult cave bears is less certain. The size and mass of a fully grown male cave bear likely placed it outside the profitable prey range for even a large cave lion. The risk of injury from the bear's claws and crushing bite force would have outweighed the caloric benefit in most circumstances. But interactions between these 2 species, territorial conflicts over cave entrances, confrontations over carcasses, the lion assessing the bear and the bear assessing the lion, must have been a regular feature of Ice Age European life. The spotted hyena, Crocuta spelaea, the cave hyena, was another major player. Modern spotted hyenas are formidable animals whose social hunting behavior and extraordinary bite force allow them to exploit resources that other predators cannot access. Their Pleistocene European counterparts were comparable in size to their modern African relatives, and fossil sites across Europe contain accumulations of bones that bear the distinctive tooth marks of hyena gnawing, evidence of animals stripping every caloric remnant from large carcasses. Cave hyenas and cave bears would have competed directly for cave spaces, and there is fossil evidence from multiple sites of hyenas gnawing cave bear bones, though whether these represent predation on live bears or scavenging of bears that had already died during hibernation is difficult to determine. The woolly rhinoceros. The straight-tusked elephant, which during warmer interglacial periods moved northward into Europe in enormous numbers, creating forests that must have resembled something between a modern temperate woodland and a subtropical jungle. The giant deer, the steppe bison, the aurochs. This was a landscape crowded with megafauna in a way that has no parallel anywhere on Earth today. The closest modern analogy, the African savanna, is a pale shadow of the biological density that characterized Pleistocene Eurasia at its peak. And yet, within this crowd of giants, the cave bear occupied a position that was simultaneously powerful and surprisingly specific. It was powerful because of its size, its strength, and the fact that adult males had essentially no natural predators. No predator in Ice Age Europe was reliably capable of taking a healthy adult male cave bear. The cave lion might harass one, a pack of cave hyenas might attempt to mob an old or sick individual, but a prime adult male cave bear, 500 kilograms of muscle and fat, with forelimbs capable of generating force that no contemporary predator could easily counter, was, for practical purposes, invulnerable. It was specific because of its extraordinary dependence on caves. Unlike woolly mammoths, who were broadly distributed across open landscapes, unlike cave lions, who moved over vast territories following prey, unlike wolves, who could den in almost any sheltered location, the cave bear was tethered to specific geological features. It needed limestone karst landscapes, the type of geology that creates cave systems. It needed those cave systems to be in the right temperature range. It needed them to be accessible but sheltered, and it needed them to be available every single autumn, year after year, without fail. In a stable world, in a world where the landscape changed slowly over thousands of years, this was not a constraint. The karst landscapes of Europe are vast. The cave systems they contain number in the thousands. There was, for most of the cave bear's 300,000-year history, more than enough cave for every bear. But the world of the late Pleistocene was not a stable world. It was a world in the middle of one of the most dramatic environmental upheavals in recent geological history. A world of advancing ice sheets and retreating forests, of river systems changing course and mountain passes opening and closing with the seasons, of landscapes that could look profoundly different within a single human lifetime, let alone across the timescales over which evolution operates. And into this already stressed and shifting landscape, somewhere between 45,000 and 40,000 years ago, a new species arrived in Europe. They came from the east. They moved along river valleys and coastlines, following the distribution of prey animals. They carried tools made of flint and bone. They wore clothing. They made fire reliably and deliberately. They communicated in ways that allowed complex information to be transmitted across generations. They were Homo sapiens, and within 20,000 years of their arrival, the cave bear was gone. Before we talk about what humans did to the cave bear, we need to talk about what humans found when they arrived in Europe, because the Europe that Homo sapiens entered between 45,000 and 40,000 years ago was not empty. It was not a blank slate waiting to be written on. It was a landscape already occupied, deeply, thoroughly, anciently occupied, by a community of large mammals that had been evolving in place for hundreds of thousands of years. Animals that knew this landscape in a way that no newcomer could. Animals that had refined their survival strategies across geological timescales. And among all of these animals, none was more deeply embedded in the physical fabric of the European landscape than the cave bear. The humans who arrived in Europe during this period are known to us today as Cro-Magnons, a name derived from the rock shelter in the Dordogne region of France, where their remains were first formally described in 1868. But that name, with its faint suggestion of primitiveness, is deeply misleading. These were not crude, stumbling proto-humans feeling their way through a hostile world. They were fully modern Homo sapiens, cognitively, anatomically, behaviorally, indistinguishable from people alive today. They had language, they had art, they had sophisticated social structures and long-range trade networks that moved obsidian, shell, and ochre across hundreds of kilometers. They had, in short, everything that makes our species uniquely dangerous. They also arrived into a Europe that already had humans in it. Neanderthals, Homo neanderthalensis, had been living in Europe for over 300,000 years. They were not the slouching, dim-witted caricatures of 19th century imagination. They were intelligent, adaptable, and deeply experienced inhabitants of Ice Age Europe. They made tools. They buried their dead. They used pigments. They had fire. And they had their own complex relationship with the cave bear, one that predated the arrival of Homo sapiens by geological ages. The evidence for Neanderthal interaction with cave bears is among the most debated and fascinating topics in all of Pleistocene archaeology. At the site of Bruniquel Cave in southern France, archaeologists discovered in 2016, in a paper published in Nature that sent shockwaves through the paleoanthropological community, a structure built deep inside the cave, over 300 meters from the entrance, in complete darkness. The structure was made from broken stalagmites, arranged into roughly circular and oval formations. It had been deliberately constructed. Radiocarbon and uranium-thorium dating placed its age at approximately 176,000 years ago, far too old to be the work of Homo sapiens, who had not yet arrived in Europe. The builders were Neanderthals. The purpose of the structure remains unknown, but its location, deep inside a cave system in a zone that cave bears also used, raises questions that archaeologists are still debating. Was it a place of ceremony? A functional shelter? Evidence of Neanderthal activity in a realm that was otherwise dominated by bears? More directly relevant is the evidence from sites like Potočka Zijalka in Slovenia and Drachenloch in Switzerland, where cave bear bones have been found arranged in ways that some researchers have interpreted as deliberate, non-utilitarian placement by Neanderthals. The Drachenloch site, discovered by the Swiss paleontologist Emil Bachler in the 1920s, yielded cave bear skulls apparently arranged on stone shelves or in stone cists, leading Bachler and subsequent researchers to propose that Neanderthals were conducting some form of bear cult, ritual behavior centered on the cave bear. This interpretation has been vigorously challenged. Many modern archaeologists argue that the arrangements at Drachenloch can be explained by natural processes, by water movement, sediment shifting, the simple accumulation of bones in spaces where they happen to come to rest. The debate has not been definitively resolved, and it probably cannot be resolved with the evidence currently available. What is clear is that Neanderthals and cave bears shared cave spaces repeatedly, and that the relationship between them was close enough and consistent enough to leave a detectable signature in the archaeological record. When Homo sapiens arrived, they stepped into this pre-existing relationship, and they brought something to it that Neanderthals had never possessed in quite the same way. Systematic, large-scale, coordinated hunting technology. The Upper Paleolithic Revolution, the explosion of cultural and technological complexity that accompanies the arrival of modern humans in Europe, is one of the most dramatic transitions in the entire archaeological record. In the space of a few thousand years, the archaeological signature of human activity in Europe transforms completely. Blade tool technologies replace older, less standardized, flaking traditions. Bone, antler, and ivory are worked into projectile points, needles, and ornaments. Fired clay figurines appear. Musical instruments appear. Bone flutes from the Swabian Alb in Germany, dated to over 40,000 years ago, are among the oldest known musical instruments on Earth. And caves across France, Spain, Germany, Romania, and beyond begin to fill with art. The art matters for our story, not just aesthetically, evidentially, because Paleolithic cave art is, among other things, a record of the animals that Homo sapiens encountered, observed, and cared about enough to paint by firelight on stone walls deep underground. The Chauvet Cave in the Ardèche region of France, with paintings dated to over 36,000 years ago, contains what many researchers consider the greatest single collection of Paleolithic animal art on Earth. Rhinoceroses, mammoths, cave lions in extraordinary detail, horses, bison, aurochs, bears. The bears depicted at Chauvet and other sites show a level of observational accuracy that is striking. Artists who painted these animals had clearly spent time watching them closely. The proportions, the postures, the specific morphological details visible in the paintings are consistent with accurate representation rather than schematic symbol-making. These were people who knew bears, who had seen bears, who had thought carefully about bears. And there is evidence, from the Chauvet Cave specifically, that these artists were not simply passive observers. The floor of the Chauvet Cave is covered in cave bear remains. Skulls, long bones, phalanges, the bones of animals that died in the cave across thousands of years of use as a denning site. And among these bones, archaeologists have found evidence of human activity: hearths, stone tools, the charcoal traces of torches. Humans were inside this cave. Humans who were surrounded by the physical remains of cave bears, some of which may have still been alive in adjacent chambers when the artists worked. At one point in the Chauvet Cave, a cave bear skull sits on a large fallen rock in the middle of a chamber. It has been placed there, positioned deliberately, balanced on the flat surface of the rock, facing outward. Whether this was a ritual act, a territorial marker, an expression of something we lack the cultural framework to interpret, we cannot say with certainty. But it was not accidental. Something deliberate was happening in that chamber, between humans and the bones of bears. This is the context into which we need to place the question of whether humans hunted cave bears. For many decades, the assumption was that they did not. The reasoning was ecological. Cave bears were large, powerful, and apparently not particularly nutritious given their heavily vegetarian diet. A herbivore's flesh is typically leaner and lower in the specific fatty acids that Ice Age hunters most needed. Cave lions and hyenas were the cave bears' real ecological competitors, this argument went. Humans simply used the caves at different times, avoided live bears when possible, and occasionally scavenged or made use of bears that had died during hibernation. This view has been progressively eroded over the past 2 decades by a growing body of archaeological evidence. The most direct evidence comes from cave bear bones bearing cut marks. the distinctive, fine linear grooves left by stone tools when hominids process a carcass. Cut marks on animal bones are among the most reliable indicators of human hunting or butchering activity because they have a characteristic appearance that distinguishes them from carnivore tooth marks, from root etching, from geological abrasion. Under microscopic analysis, cut marks from stone tools are unmistakable, and on cave bear bones from multiple European sites, cut marks have been found. At the site of Hohle Fels in southwestern Germany, the same cave that yielded the oldest known figurative art, a tiny ivory carving of a lion-headed human figure dated to over 40,000 years ago, cave bear bones with cut marks have been recovered from auricnation levels, the earliest cultural layer associated with modern humans in Europe. At Vogelherd Cave, also in the Swabian Alb, similar evidence has been documented. At sites in Romania in the Carpathian region, where some of the densest cave bear fossil accumulations in Europe are found, analysis of bone assemblages has revealed patterned cut mark distributions consistent with systematic butchering rather than opportunistic scavenging. A comprehensive study published in the Journal of Human Evolution in 2012, analyzing cut mark frequencies and distributions across cave bear assemblages from multiple Central European sites, concluded that human exploitation of cave bears, both through hunting and through processing of naturally dead individuals, was a regular and persistent behavior, rather than an occasional opportunistic event. But hunting cave bears presented challenges that hunting reindeer or horses did not. A reindeer can be driven into a river crossing and speared from the bank. A horse can be stampeded over a cliff edge by a coordinated group of hunters on a landscape where such features exist. These are tactics that appear clearly in the archaeological record, in kill sites, in the distribution of bones at cliff bases, and the remains of animals processed in large numbers at specific locations. A cave bear is a different problem entirely. First, there is the size. A healthy adult male cave bear was not an animal you killed with a single spear thrust. The hide was thick. The musculature was extraordinary. The skeletal structure was robust in ways that protected vital organs. Killing a cave bear required either a fortunate shot into the throat, the armpit, the gap between ribs that exposed the heart and lungs, or sustained engagement with an animal that could kill a human with a single blow of its forelimb. Second, there is the behavior. Cave bears were not browsing quietly in open meadows. They were concentrated in specific locations, the caves, during the most vulnerable period of their annual cycle. A hibernating cave bear was technically an easier target than an active one, but reaching a hibernating bear deep inside a cave system in complete darkness with whatever torch technology was available, and then killing it without triggering a defensive response from an animal that, even half asleep, weighed several hundred kilograms, this was not a trivial undertaking. There is a reason that bear hunting, across virtually every human culture that has practiced it, has been surrounded by ritual, ceremony, and carefully maintained protocols. From the Ainu people of Japan to the indigenous peoples of Scandinavia and Siberia, bear hunting was not simply an economic activity. It was a transaction between humans and something that the hunters understood to be on a fundamentally different level from ordinary prey, something that required acknowledgement, propitiation, respect. We cannot know whether the Cro-Magnons who hunted cave bears felt something analogous. We have no direct access to their beliefs, their ceremonies, their songs. But we have the art. We have the placed skull in the Chauvet Cave. We have the arrangements at Drachenloch, whatever they actually represent. And we have a pattern, visible across the archaeological record of Upper Paleolithic Europe, of humans engaging with cave bears in ways that go beyond simple predator-prey economics. Something about the cave bear mattered to these people in a way that went beyond calories. which makes what happened next all the more significant. Because the archaeological record of cave bear bones in European sites begins to change around 40,000 years ago. Not dramatically, not all at once. The cave bear was still present, still widespread, still leaving its bones and its claw marks in cave systems across the continent. But the numbers begin to shift. The density of cave bear remains in archaeological sites with strong human occupation signals starts to decline relative to sites without strong human occupation. The pattern is not universal, and it is not clean. The fossil record is never clean. But the trend, analyzed across multiple sites and multiple researchers, points in a consistent direction. Humans were moving into the caves, and the cave bears were beginning, slowly, to lose ground. But here is where the story becomes genuinely complicated. Because if the cave bear's decline were simply a story of human hunters killing bears until none were left, the pattern in the fossil record would look different from what it actually shows. A hunting-driven extinction typically leaves a signature of rapid decline concentrated in a geographically expanding wave. The human frontier of arrival followed closely by megafaunal collapse. Think of the extinctions in Australia, where the arrival of humans around 65,000 years ago was followed within a geologically short period by the disappearance of the giant marsupials. Think of the extinctions in the Americas, where the arrival of Clovis hunters around 15,000 years ago was followed by the rapid collapse of the Pleistocene Megafauna. The cave bear's decline does not look like that. It looks slower, more complicated, geographically uneven in ways that suggest multiple interacting pressures rather than a single cause. There are cave systems in the Iberian Peninsula where cave bear bones persist in the record until 24,000 years ago, close to the last glacial maximum, long after humans had been present in the region. There are sites in the Carpathians where bear populations seem to have fluctuated dramatically across millennia, contracting and partially recovering in patterns that track climate oscillations as much as human activity. Something else was happening alongside the hunting, something that was reshaping the cave bear's world at the most fundamental level. The climate was changing, and for an animal as exquisitely tuned to a specific ecological niche, the limestone cave systems of temperate Europe, surrounded by productive vegetation with stable thermal environments for hibernation, climate change was not an inconvenience. It was a physiological crisis. To understand why, we need to go back to those teeth. The teeth of the cave bear tell a story that bones alone cannot. Pick up a cave bear molar, and if you visit the Natural History Museum in Vienna or the Senckenberg Museum in Frankfurt, you can stand close enough to one to see the detail clearly. And look at the surface. What you see is not the sharp, blade-like cutting edge of a carnivore's tooth. It is not even the relatively simple bumped surface of an omnivore's molar, like the teeth of a modern brown bear. What you see is something intricate, deeply folded, a complex landscape of ridges and valleys pressed into the enamel surface, designed to maximize the grinding contact area between upper and lower molars. These teeth were built for one purpose: to process enormous quantities of tough, fibrous, abrasive plant material. Day after day, season after season, year after year. And that specialization, that extraordinary commitment to a herbivorous diet and a body the size of a small car, was ultimately the cave bear's greatest vulnerability. Here is the problem. Plants are not evenly distributed across time and space. They respond to temperature, to precipitation, to soil chemistry, to the length of the growing season, to the composition of the atmosphere. A plant community that thrives in one set of climatic conditions can collapse, shift, or transform into something entirely different when those conditions change. And during the late Pleistocene, during the final 40,000 years of the cave bear's existence, the plant communities of Europe were not stable. They were in a state of profound, repeated, and ultimately catastrophic reorganization. The mechanism driving this reorganization was the last glacial cycle. The ice sheets that had been advancing and retreating across Europe for hundreds of thousands of years were, between approximately 30,000 and 20,000 years ago, approaching their maximum extent. The last glacial maximum, the point at which the ice sheets reached their greatest coverage, occurred approximately 21,000 years ago, roughly 3,000 years after the last cave bear bones appear in the fossil record. But the environmental pressures that accompanied the approach to this maximum were already intensifying thousands of years before the ice reached its peak. As temperatures dropped and ice sheets expanded southward, the vegetated zones that supported cave bear populations were compressed. The temperate woodland and mixed forest communities of Central Europe, the habitats most productive for large herbivores dependent on roots, tubers, and seasonal vegetation, retreated southward and contracted into refugia. Refugia are the isolated pockets of relatively favorable habitat that persist within a broadly hostile landscape, and they are critically important in the story of Pleistocene extinctions because they represent both the lifeline and the bottleneck through which many species were forced during glacial maxima. For the cave bear, refugia were not simply ecological sanctuaries. They were also necessarily cave-rich landscapes. Because without suitable cave systems, the refugia were useless. A patch of productive forest in a limestone karst landscape was ideal cave bear habitat. A patch of equally productive forest sitting on granite or sandstone, rock types that do not form the solution caves that cave bears required, was inaccessible. The cave bear could not simply follow its food into every available patch of landscape. It could only follow its food into landscapes that also happened to contain the geological infrastructure it depended on for survival. This geographical constraint, invisible during periods of climatic stability when suitable habitat was broadly available, became increasingly significant as climate deteriorated. The overlap between productive vegetation and suitable cave geology was shrinking. The effective range available to cave bears was shrinking faster than simple temperature maps would suggest. Paleogenetic research, the analysis of ancient DNA extracted from cave bear fossils, has allowed researchers to map this contraction in remarkable detail over the past 15 years. Studies published by research groups, including those led by Axel Barlow at the University of Potsdam and Axel Janke at the Senckenberg Biodiversity and Climate Research Center, have used mitochondrial and nuclear DNA from dozens of cave bear specimens to reconstruct the population structure and demographic history of the species across its final millennia. What they found is a story of fragmentation. In the periods predating approximately 50,000 years ago, cave bear populations across Europe show relatively high genetic diversity and evidence of gene flow. Individuals from different regions were, at least occasionally, interbreeding, maintaining the genetic connectivity that keeps a species healthy and adaptable. But as you move forward in time through the fossil record, the genetic picture changes. Populations become more isolated. The genetic signatures of different regional groups diverge. The evidence of gene flow between populations diminishes and eventually disappears. By 30,000 years ago, cave bear populations in different parts of Europe were essentially isolated from each other. The bears in the Iberian Peninsula were genetically distinct from the bears in the Carpathians. The bears in the Alps were distinct from both. Each regional population was an island, surrounded not by water, but by unsuitable habitat that prevented movement and genetic exchange. Isolated populations are fragile populations. When a population is small and isolated, random demographic events, a particularly hard winter, a disease outbreak, a run of poor berry harvests, can drive it to local extinction. And local extinctions, in a species where regional populations are isolated from each other, cannot be rescued by immigration from elsewhere. Each loss is permanent. This is the process that paleoecologists call population fragmentation, and it is one of the classic precursors to extinction. The total number of individuals in a species may still be substantial. The species may not yet look like it is in trouble from a distance, but the internal structure of the population has already become dangerously brittle. It is a species that has lost the resilience to absorb further shocks. And the further shocks were coming. Now we return to those
Because the dietary specialization of the cave bear was not just a vulnerability in the abstract sense of limiting habitat range, it was a vulnerability in a much more immediate physiological sense. And the evidence for this vulnerability is written in the bones of cave bears who died during hibernation, the animals whose remains fill the floors of European cave systems in their thousands. Paleopathological analysis, the study of disease and physiological stress in fossil remains, has been applied to cave bear assemblages from multiple sites over the past 3 decades, and the results are striking. Researchers including Gernot Rabeder of the University of Vienna and colleagues working on the massive Conturines cave assemblage in the Italian Dolomites have documented extraordinarily high frequencies of pathological bone conditions in cave bear remains. Dental disease is rampant, not just the wear that comes from a lifetime of processing abrasive vegetation, though that wear is dramatic and consistent across populations, but active pathological conditions, caries, abscesses, periodontal disease that has spread into the jawbone itself, creating cavities and fistulae visible in the fossil material. Some individuals show evidence of dental disease so severe that large portions of the jaw are affected, with bone resorption and infection traceable even in material tens of thousands of years old. Think about what severe dental disease means for an animal that depends entirely on its ability to chew and grind large quantities of plant material. It means reduced food intake. It means reduced fat deposition in the pre-hibernation period. It means an animal entering winter with insufficient reserves. It means death during hibernation, quietly, without drama, in the darkness of a cave that the bear may have used every year of its life.
Beyond dental pathology, the Conturines assemblage and others show elevated frequencies of metabolic bone disease, osteoporosis, bone mineral depletion, stress fractures, consistent with nutritional deficiency during hibernation, when the bear's body mobilizes calcium and other minerals from the skeleton to maintain physiological function during the long fast. In modern bears, this process is tightly regulated and causes minimal long-term skeletal damage. In cave bears, the evidence suggests it was sometimes going wrong. Animals depleting their skeletal reserves beyond the point of recovery, emerging from hibernation in a compromised state, or not emerging at all. A study published in Historical Biology in 2014, analyzing stable carbon and nitrogen isotopes in cave bear remains from Austrian and Romanian sites across different time periods, found a statistically significant trend. Cave bears from deposits closer to the extinction horizon, from the period between roughly 30,000 and 24,000 years ago, show isotopic signatures consistent with dietary stress. Lower overall caloric intake. Greater variability between individuals, suggesting inconsistent access to food resources. In some populations, a subtle shift in the isotopic profile suggesting that some individuals were supplementing their diet with small amounts of animal protein, possibly insect larvae, carrion, eggs,
in a way that earlier, apparently nutritionally secure populations did not. This is an animal trying to adapt. An animal whose extraordinarily specialized teeth and gut were built for processing enormous quantities of plant material, now living in a landscape that could no longer reliably provide that material in the quantities required. An animal whose body was essentially too well designed for a world that was disappearing. The irony is precise and painful.
The very features that had made the cave bear so successful for 300,000 years, the commitment to herbivory, the extreme hibernation physiology, the dependence on specific cave environments, were now liabilities in a world that was changing faster than evolution could respond. Evolution operates across generations. It requires genetic variation and differential reproductive success across timescales of centuries to millennia before meaningful morphological change occurs. The climate changes of the late Pleistocene were happening on timescales of decades to centuries. The fragmentation of cave bear populations was reducing the genetic variation that evolution requires as its raw material. The combination of these factors meant that the cave bear had no evolutionary escape route. It could not rapidly evolve a more flexible diet. It could not rapidly evolve the ability to den in non-cave environments. It was locked in, by its own extraordinary success, to a set of biological commitments that the changing world could no longer honor. And into this already compromised situation, the human pressure was intensifying, not just hunting pressure, something more fundamental than that. Space. The cave systems of Ice Age Europe were not infinite resources. They were specific, mappable, countable locations, limestone formations that had been shaped over millions of years into the particular configurations that made them habitable. And both cave bears and humans needed them. Not for the same reasons. Humans did not hibernate, did not require the thermal stability deep in the cave that bears depended on. But both species were using these spaces, and their use was not compatible. A cave occupied by humans, with its fires, its noise, its smells, its persistent human presence, was a cave that cave bears could not easily use. Not because humans would necessarily kill every bear that approached, but because bears, even very large ones, are sensitive to disturbance during hibernation. An animal roused from deep hibernation in midwinter, even just roused to alertness by unfamiliar sounds or smells without fully waking, burns energy reserves that it cannot replace until spring. Repeated disturbance across a winter can mean the difference between an animal that emerges in spring lean but viable and one that does not emerge at all. Paleoecological modeling studies, including work published in the journal Scientific Reports in 2019 by a team including researchers from the University of Vienna and the Max Planck Institute for Evolutionary Anthropology, have attempted to quantify the relative contributions of climate change and human competition to cave bear extinction. Their models, built using radiocarbon-dated fossil occurrence data, paleoclimate reconstructions, and estimates of human population density from archaeological site distributions, suggest something important. Neither climate change alone nor human pressure alone is sufficient to explain the timing and pattern of cave bear extinction, but the two pressures together, operating simultaneously on a population that had already been fragmented and nutritionally stressed, produce a model output that closely matches the observed pattern of cave bear decline and disappearance. The cave bear was not simply hunted out of existence. It was squeezed. Squeezed from one side by a climate that was dismantling the vegetation communities it depended on. Squeezed from the other side by a species that was systematically occupying the cave systems it needed for survival. Squeezed genetically by population fragmentation that was eroding its capacity to adapt. Squeezed physiologically by the ancient commitments of its own biology. The last cave bears would have felt none of this as a narrative. They had no concept of extinction, no awareness that their kind was ending. An old female, her teeth worn almost smooth after 20 or 25 years of grinding vegetation, dragging herself into the back of a cave in the Carpathian Mountains sometime around 24,000 years ago, was simply doing what her biology told her to do, finding the cool, stable dark, settling into the earth, slowing her breathing, waiting for a spring that, for her and for her kind, would not come. But the story does not end there, because the cave bear did not simply vanish without a trace, leaving nothing behind but its bones and its claw marks on cave walls. Its disappearance had consequences for the ecosystems it had shaped, for the humans who had lived alongside it, and for the science that would spend the next 200 years trying to understand what it had been. And there is one more twist in this story, one more layer that only the very latest science has revealed, a layer that involves genetics, hybridization, and the possibility that the cave bear is not quite as gone as we thought. In 2018, a paper was published in the journal Nature, Ecology, and Evolution that quietly rewrote a portion of bear evolutionary history. The authors, a team of paleogeneticists led by Axel Barlow, working with ancient DNA extracted from cave bear fossils across multiple European sites, had been doing what paleogenetics does best. They were reading the molecular record preserved in ancient bones, sequencing fragments of nuclear DNA, piecing together genomes from material tens of thousands of years old, and comparing what they found against the genomes of living bears. What they found was not what anyone had expected. Embedded in the genomes of modern brown bears, the living species that today occupies much of the same range that cave bears once dominated, were segments of DNA that did not belong there. Segments that, when compared against the cave bear genome sequences the team had reconstructed, matched. Not partially, not ambiguously. They matched in ways that could only be explained by one mechanism. At some point during the late Pleistocene, cave bears and brown bears had interbred. The two species had been hybridizing. Take a moment to absorb what that means. These were not closely related subspecies of the same animal. Cave bears and brown bears had been on separate evolutionary trajectories for approximately 1.2 million years. They were as different from each other in terms of time since divergence as modern humans are from Homo erectus. Their diets were different. Their physiology was different. Their skeletal morphology was different, enough that any trained paleontologist could distinguish a cave bear bone from a brown bear bone at a glance. They were, by any reasonable definition, genuinely distinct species. And yet, they were meeting and mating and producing offspring that survived and reproduced. This kind of interspecies hybridization is, it turns out, far more common in mammalian evolution than classical taxonomy ever suggested. The genomic revolution of the past 20 years has revealed hybrid signatures in the genomes of living species across the tree of life, in big cats, in wolves, in cetaceans, in primates. Neanderthal DNA persists in the genomes of all modern humans with non-African ancestry, at levels of 1 to 4%. Denisovan DNA persists in the genomes of modern populations across Oceania and parts of Asia. The boundaries between species are permeable in ways that 2 decades of genomic research have made undeniable. For bears, the picture is particularly complex. Brown bears and polar bears, species separated by a comparable evolutionary distance to cave bears and brown bears, are known to hybridize in the wild today, producing fertile offspring called Pizzly bears or growler bears. The genomic signature of ancient hybridization between polar bears and brown bears is detectable in modern polar bear populations. The bear family, it appears, has always been a family with unusually permeable species boundaries. But what the 2018 Barlow study revealed for cave bears and brown bears went beyond a simple record of occasional hybridization. The team found that the cave bear genetic material present in modern brown bears was not randomly distributed across the genome. It was concentrated in specific regions, and some of those regions were associated with genes involved in metabolic function and how an organism processes and stores energy. The implication is significant, though the researchers were careful to frame it with appropriate caution. The metabolic genes that cave bears contributed to brown bear populations may have been adaptive. Brown bears living in environments similar to those that cave bears had occupied, with long winters, pronounced seasonal food availability, and selective pressure for efficient hibernation, may have benefited from incorporating cave bear metabolic adaptations into their own genetic toolkit. The hybridization was not simply a biological accident. It may have been, in the language of evolutionary biology, a form of adaptive introgression, the selective incorporation of useful genetic material from one species into another through hybridization. If this interpretation holds up under further analysis, and the researchers were clear that much work remains to be done, it means something remarkable. It means that the cave bear, though extinct as a distinct species, did not disappear entirely from the biological world. A portion of its genome, fragments of its 300,000-year evolutionary history, survived the extinction. Not in any living cave bear, because there are none, but woven into the DNA of the brown bears that replaced it, present right now in the genome of every European brown bear, every Siberian brown bear, every Alaskan grizzly that carries the genetic legacy of this ancient hybridization. The cave bear is gone, but it is not entirely absent. This is a nuance worth sitting with, because extinction is often presented as a binary. A species exists, and then it does not. The genomic evidence increasingly suggests that the reality is more complicated, that species can end while still leaving biological echoes, that the boundaries between existence and non-existence at the molecular level are not always as clean as the fossil record alone would suggest. But ancient DNA has given us more than just the hybridization story. It has given us something equally valuable, a window into the cave bear's final centuries that no amount of bone analysis alone could provide. The demographic history of the cave bear, reconstructed from ancient genomic data across multiple studies published between 2015 and 2022, paints a portrait of a species in progressive crisis. Using a mathematical technique called the pairwise sequentially Markovian coalescent, a method that uses patterns of genetic variation within a genome to infer historical changes in population size, researchers have been able to reconstruct the effective population size of cave bears across hundreds of thousands of years. The results show a species that was already in decline long before the arrival of Homo sapiens in Europe. Cave bear effective population sizes show evidence of contraction beginning roughly 50,000 years ago, coinciding with the onset of the climate deterioration that preceded the last glacial maximum, and with the period during which Neanderthals were themselves under increasing ecological pressure. This early decline, predating modern human arrival by 5,000 to 10,000 years, is important. It tells us that the cave bear was not simply a healthy, thriving species ambushed by a sudden external shock. It was already a species on a downward trajectory when the additional pressures of modern human competition arrived. A species whose resilience was already compromised, whose population structure was already fragmenting. whose genetic diversity was already eroding. The arrival of Homo sapiens did not initiate the cave bear's decline. It accelerated a process that was already underway. And in doing so, it pushed a species that might otherwise have persisted through the last glacial maximum, as brown bears persisted, as wolves persisted, as red deer persisted, past the point of no return. This distinction matters. It matters scientifically because it changes how we model the relative contributions of climate and human pressure to Pleistocene extinctions. And it matters philosophically because it complicates the simple narrative of human guilt that sometimes accompanies discussions of prehistoric megafaunal extinction. The cave bear's story is not a straightforward tale of human destruction. It is a story of confluence, of multiple pressures arriving simultaneously at a moment of maximum vulnerability. Climate, diet, geology, genetics, and human competition all played roles. None of them alone is sufficient. All of them together are necessary. Now, let us talk about the discovery of the cave bear. Because the scientific story of this animal, how we came to know it, how our understanding of it has shifted across 2 centuries of research, is itself a remarkable narrative. The first formal scientific description of cave bear remains was published in 1794. The author was Johann Christian Rosenmüller, a German anatomist working in Leipzig, and the material he was describing came from a cave near Gehlenruth in what is now Bavaria, a site that had been yielding enormous quantities of strange, unfamiliar bones for decades. Local people had been finding these bones for generations, long before any scientific framework existed to interpret them. In medieval and early modern Europe, the enormous skulls and bones of cave bears were interpreted through the lens of the available cultural mythology. They were the bones of dragons, of giants, of creatures from a world before the flood. The name Drachenhöhle, dragon cave, attached to multiple Central European cave sites, is not coincidental. It reflects centuries of local tradition in which these enormous, inexplicable bones were integrated into the only explanatory frameworks available to people who had no concept of geological time or biological extinction. Rosenmüller's formal description established the cave bear as a distinct species, though he initially placed it within the genus Ursus alongside living bears, a classification that has remained essentially stable to this day. The name spelaeus, from the Latin for cave, was formalized by the German geologist Georg August Goldfuss in 1823, giving us the binomial Ursus spelaeus that scientists still use. But the early 19th century understanding of the cave bear was limited in a fundamental way. Not by lack of material, cave bear fossils were, even then, among the most abundant Pleistocene mammal remains available to researchers. The limitation was conceptual. The intellectual framework of the time had not yet fully absorbed the implications of deep geological time, of biological extinction, of evolution. Cave bear bones were fascinating anomalies, animals clearly related to living bears, but demonstrably different, clearly ancient, but of uncertain age. It was the work of the 19th century's greatest geological minds, Cuvier in France, Buckland in England, Lyell across both countries and beyond, that gradually built the conceptual infrastructure needed to make sense of creatures like the cave bear. Cuvier's demonstration that extinction was a real biological phenomenon, not a philosophical impossibility, was foundational. His analysis of cave bear material contributed to his broader argument that the Earth had been inhabited by creatures now entirely gone, a revolutionary idea in an intellectual environment still largely shaped by biblical natural history. William Buckland's 1823 monograph on Kirkdale Cave in Yorkshire, a site that had yielded hyena and other Pleistocene mammal bones in abundance, established the methodology of reading the ancient ecological story encoded in cave bone assemblages. Buckland understood that the bones in these caves were not random accumulations. They were the records of lives lived, of deaths occurring, of ecological relationships between species that no longer existed. He was, in a real sense, the founder of the paleo-ecological detective tradition that still drives cave bear research today. The 20th century brought new tools and new scales of analysis. Radiometric dating, first radiocarbon dating, then uranium series dating and other methods that extend further back in time, allowed researchers to move from relative chronologies to absolute dates. The cave bear's extinction horizon could be fixed with increasing precision. The temporal relationship between cave bear decline and human arrival could be examined quantitatively rather than simply assumed. Isotope geochemistry transformed dietary reconstruction. KT scanning of fossil skulls allowed biomechanical analysis without destructive sampling. And then, in the 2000s and 2010s, ancient DNA arrived and rewrote the story again, adding the population history, the hybridization record, the demographic trajectories that no other method could access. Each new technique has added resolution to the picture. Each has revealed complexity that earlier, simpler accounts missed. And each has reinforced a conclusion that is now, among researchers who work on this material, essentially a consensus. The cave bear was one of the most ecologically and evolutionarily distinctive large mammals in the history of Europe. Its herbivorous diet and a body built for imposing physical dominance, its extraordinary dependence on limestone cave systems that linked its biology to specific geological landscapes, its 6-month hibernation cycle that made extraordinary metabolic demands and left it uniquely vulnerable to any disruption of its food supply or its cave access. Its 300,000-year tenure as one of the dominant large mammals of an entire continent. And its extinction. The convergence of climate, competition, fragmentation, and the relentless, systematic pressure of a cognitively modern primate that needed the same caves and understood, however dimly or however profoundly, that the enormous bear sleeping in the darkness at the end of the tunnel was simultaneously an obstacle and a resource. The cave bear lost that negotiation, and Europe has never seen anything quite like it since. But here is what we still do not know. Here is where the scientific story remains genuinely, productively open. We do not know the precise mechanism by which the last cave bear populations went extinct. We have models, we have probability distributions and statistical confidence intervals and carefully hedged conclusions, but we do not have the equivalent of a smoking gun, a sight, a moment, a definitive event that we can point to and say, here, this is where it ended. The extinction horizon for cave bears, while broadly constrained to between 28,000 and 24,000 years ago across most of Europe, remains imprecise. The last population may have persisted somewhere in a Carpathian or Iberian refugium until a date we have not yet pinned down. We do not fully understand the hybridization story. The Barlow 2018 paper established that it happened and suggested where in the genome the evidence is strongest. But the when, the where, the how frequently, and the full functional significance of the cave bear genetic material that persists in modern brown bears, these questions are actively being worked on. We do not know whether Neanderthals hunted cave bears systematically, or whether the arrangements of bear skulls and bones at sites like Drachenloch represent ritual behavior, functional storage, or the meaningless work of gravity and time. This debate has been running for a century and is not close to resolution. And we do not know, perhaps most intriguingly, what the cave bear's extinction meant ecologically for the cave systems of Europe. Cave bears were not passive residents of these spaces. They modified them. They dug. They scratched. They deposited enormous quantities of organic material in the form of droppings and urine and the remains of food. They created microhabitats. They may have influenced the distribution of other cave-dwelling species in ways that we have barely begun to examine. When they disappeared, something changed in those caves. Some ecological function ceased. Some niche opened. Some relationship ended. We have almost no understanding of what that meant for the broader cave ecosystem. These are not trivial questions. They are the questions that keep researchers returning to cave sites across Europe every field season. Returning with better sequencing technology, better dating methods, better biomechanical models. Returning to the darkness where the cave bears left their bones and their claw marks, and trying, from those fragments, to reassemble a world. The bones are still there. In Austria and Romania and Spain and Germany and France and Slovenia, in museums and in the ground, in display cases and in the backs of unexplored cave chambers that no human has entered since the last cave bear clawed its way inside. Tens of thousands of individual animals, represented in the fossil record in numbers that no other Pleistocene megafaunal species can match. The cave bear does not lack for physical traces. It lacks, still, for complete understanding. And that gap between the extraordinary abundance of the evidence and the questions that evidence still cannot answer is exactly what makes this animal one of the most compelling subjects in all of Pleistocene biology. The extraordinary abundance of the evidence and the questions that evidence still cannot answer is exactly what makes this animal one of the most compelling subjects in all of Pleistocene biology.